chapter. Chapter 1 is about sets and logics. This will be quite fundamental objects in mathematics. Set. Yeah, basically, everything is like a set. The first section, sets. So what is a set? It is just a collection of objects. So a set is a collection of objects. It's a collection of objects. You just collect a bunch of things and then make it a set. Oh yeah, by the way, today's lecture will be a lot of definitions. Probably you already know, so it can be a little boring. So the objects in this set, in a set, are called elements. Sets, so basically sets have elements. Yeah, so maybe example. And the common way to write set is use this curly brace. So this is a set with how many elements? Four elements. And they are 1, 2, 3, 4. And it doesn't have to be just numbers. Everything you can just say. It's again an integer, but maybe pi, e, or some letters, anything. Or you can mix them together, a1, pi, I don't know. You can make anything as a set, like this. And common convention for set is that a set is just determined by its element. Determined only, let's say, only by its element. What does that mean? Elements. We only care whether this is an element of this set or is this an element of this set, something like that. We don't want to consider how many of these are there. Just if this is this there or not, just is a yes or no question. So, and also the order of the way I write these elements doesn't matter. They all mean the same. So what this means is order doesn't matter. Does not matter. And multiplicities does not matter. Multiplicity means the number of times that this occurs. Multiplicity does not matter either. So, for instance, let me write show you an example. For instance, 1, 2, 3. As I said, these are the same. 2, 3, 1, right? They all have the same, exactly the same elements. 1 is there, here. 2 is there. 3 there. You don't really want to consider the order, so you don't care about the order. And also, 1, 1, 2, 2, 3, they are considered to be the same set because we don't want to consider how many ones there are. Just 1. If there is one there, then it's okay. If there is 2, you don't count how many 2s there are. Just 2 is there, so they are the same. Okay. And if the set is finite like this, only a few elements, then we can simply express as curly brace by listing all of the elements. But sometimes you have to deal with infinite set. We cannot really write all integers here, or real numbers, even more difficult. So a set can be described using words. A set can be described by several ways. By listing the properties of the elements that determines the elements completely. So, for instance, A. Let's say X is a positive integer, something like this. All right, so A is a set, but I didn't define this set by listing all the elements, but I just say, it's a set of elements which are positive integers. And in this way, it is clear that which number is in A, which number is not in A, right? Is it clear to you? Is 5 in A? Is 3 over 2 in A? For every given number, you can decide whether that is in A or not. So it is a good definition. And also, X may be something like X is a real number such that X is between 0 and 1. One can define a set like this. So it gives the properties of the element. It's a real number, and it satisfies this. Or one can also, for simplicity, one can also write like this. X is an integer. So this means X is an integer in this range. So actually, there are only finitely many of these. So you can also express this set like that. They are the same. They represent the same set. Okay? All right. I'm sure that you are familiar with this. And we have frequently used sets. This will be used very often in this semester. Z, but I write Z in this way. And it is a set of all integers. X is an integer. So Z means the set of all integers. And Q is the set of rational number. And R is a real number. And we also write this kind of notation. Z minus, this means you can guess X, or we can even write something like that. X is in Z such that X is negative. So in other words, Z minus is the set of all negative integers, right? And similarly, Z plus, you can imagine X this, or something like Z greater than or equal to 0, if you want to include 0 as well, something like that. Or this is also denoted if I write non-negative integer. So these are common notation, and it will be used in this textbook and also in this lecture. And similarly, you can define Q plus or R minus, something like that. All right? These are commonly used sets. Okay. Now, more notation. If X is an element of A, yeah, we are implicitly assuming that A is a set. X is an element of A. Yeah, A must be a set. We write in this way. So yeah, X is in. Oh yeah, by the way, I already used this notation. So otherwise, if X is not an element of A, we write this way. So this means X is an element of A, or X is in A, X is not in A, etc. And if A is a finite set means it's a set with finitely many elements. If A is a finite set, we can talk about its cardinality. The cardinality of A is denoted like absolute value of A is denoted this, and the number, it is the number of elements. Yeah, if A is a finite set, maybe the most fundamental question to ask is this: what is the cardinality of this set? What is the number of elements in this set? So example, let's say A is this set, 1, 2, 3, 4. Then 3 is an element of A, 1 is an element of A, 5 is not an element of A. And what is the cardinality of A? There are 4 elements. This is going to be 4. And the square root of 3 is not an element in Q. It's not a rational number. And square root of -1, this is not an element of the set of real numbers. It's not a real number. Right, so cardinality denoted like this. And yeah, there is a special set that has nothing in it. It's called empty set. So the set with no element is called the empty set. And we write empty set usually this way, or sometimes this. They mean the same. They're the same. Empty set. This empty set notation, or this curly brace with nothing inside. So what is the cardinality of the empty set then? 0. The number of elements, there's nothing, so 0. Okay, and then we say that 2 sets are equal. 2 sets A and B are equal. What does that mean? If this is definition. We say that 2 sets are equal. When do you think that 2 sets are equal? Actually, I already mentioned. But if it satisfies, if they have the exact same elements, if they have the same elements, yeah. In other words, X is in A. This means if and only if X is in B. If this is true for every X, then they are the same set. Okay. All right. So let's see some example. 1, 2, 3. X is between 1 and 3. X is an integer. Are these 2 sets equal. Are these equal or not? They are equal. You can see they have the same elements, 1, 2, 3. And is this equal to this? Yeah, we already wrote that down. 1, 2, 3. Of course, they are not equal. 3 is here, but not here. They don't have exactly the same elements. Yeah, so but 1, 2, like I said, 1, 2, 2, they are the same set in this sense, because for everything, for every x is in this set if and only if that is in this set, right? 2 is here, 2 is here, 1 is here, 1 is here. Anything other than 1 and 2, they are not in any of this, so they are the same set. How about this? Empty set and this. Are they equal? No, they are not equal. Empty set is also kind of an object. It can be an element of a set. This is an element, a set that contains nothing. This is a set that contains one thing, which happens to be the empty set. Okay? They are different, to remember. Okay. So the question was, what is the cardinality of this set? Oh, I think that's a very good question. Cardinality of this set is the number of elements, but we don't count the multiplicities. There are only 2 elements, 1 and 2. So the cardinality of this set is 2. All right? Also here. If 2 sets are equal, then they must have the same cardinality, right? So for 2 sets, we can say that they are equal or not. But there are also other ways to compare 2 sets. So for 2 sets, even though they are not equal, we can say some things. There can be some relations between 2 sets. For 2 sets A and B, we say that A contains B. Or in other words, B is contained in A, they mean the same thing. If every element in A is also an element in B. If this condition is satisfied, then we say that A is yeah, I think I made a mistake, right? A contains B, so A must be bigger than B. Every element in B is also an element in A. Then we say that A contains B, or in other words, B is contained in A. Or, okay, let me begin. In this way, in this case, we write as follows. A contains B, something like this. Or they both mean the same thing. B is contained in A. These 2 mean exactly the same thing. You have to, there is a direction here, so this A contains. So, example, 1, 2, 3 is contained in Z, right? Because these are integers. They are all, everything in here is an element in here. This is this Z contains this. What about this? 1, 2, 3. Is this contained in -1, -2, 3? No, we can find one element that is in here that is not an element here. Everything must satisfy this. If there is even if there is only one element that doesn't satisfy this, we say that this is not true. 3 is an element also here, but 1 not here, 2 not there. So this is not. If it's not, we just write this. Okay, and there is a special name for this. If, say, A is contained in B, we also say that A is a subset of B. All right? Subset. So oh, by the way, do you think this is here is a quick question for you. Do you think this is true? The first question is this. The second question is, I'm asking you whether these are true or not. Is this true? Do you think this is true? Yes, it's true. And we will learn more about this later, but every element here is an element in here. Is that statement true? Actually, there's nothing here, so we don't need to check anything. If there is nothing to be checked, then it is automatically true. This is kind of logic that we will learn later. But just remember that empty set is a subset of anything. What about this? Is this true? Yes? Everything here is also here. They can be the same thing. It's possible they're the same thing. What about this? Also true. Because there's nothing to check. It's automatically true. So empty set is a subset of every set. Okay, so let me write down some equivalent way of writing this. So this means B is contained in A, or equivalently A contains B, or equivalently B is a subset of A, or if X B, then X is also in A. Yeah, they all mean the same thing. Okay? Oh yeah, let me give you another example. Z, the set of integers, is a subset of Q, which is a subset of R, real numbers. Is Z a subset of R plus? No, because it has an element that is not in R plus. -1 is not in here, so it's not. Any questions so far? Okay, so yeah, in the previous slide, you notice that I use this notation. This indicates that these two might be the same, but if we don't use this, so A, B means A is a subset of B, but not equal to B. So this means two things, this and this. they have to be different. And actually, I don't like this notation because sometimes it really depends on each textbook. Sometimes people include equality here without writing this, so it's also, they mean the same thing, okay, as notation. But I will use this notation just to avoid any confusion, okay? So let's say for now or this semester, these two mean the same thing. I think in the textbook, I think this is used. So yeah, in lectures at least, I'm going to always use this or this, just to make it clear that we don't include inequality, equality, okay? Is this clear? Okay. Oh yeah, let me give you another question. First one. If A, oh yeah, I will use this as well. But if I use this, it means this. But if I really want to emphasize that they are not the same, I will use this. Okay, so for now, let's use this because we learned this. I think in the textbook, this notation is also used. Just remember they mean the same thing. Then, if okay, let's vote. How many of you think that the first statement is true? Raise your hand if you think the first statement is true. Always. All right? Now, raise your hand if you think the second statement is true. Yeah. Don't look at other people. Yeah. All right. What's the difference between these two? Just if you're not sure about something, it's probably because you don't really understand the definition. In mathematics, the most important thing is to understand the definition. Without understanding definition, you cannot do anything. So what's the definition of this? A is a subset of B, but A is not equal to B. In that case, what does this mean? A is a subset of B. So if A is a subset not equal to B, is A a subset of B? Yeah, it's true. It's something like this. Okay, how can I say? Okay, it's clear, so I don't need to tell you more explanation. What about this? So it's true. It's obviously true because this condition is already included here. What about this? Is this true? If you think this is not true, can you find a counterexample for A and B? Yeah, if A equals B, let's say A equals B, both just containing just one element, 1. Is this true? Yeah, A is a subset of B. But this is not true because A is a subset of B, but because this says is that A is a subset of B, but A is not equal to B. But they are the same, so this is false. True, false, but this statement is false. We will learn more about this kind of structure. If something, then that. We will learn more about this in proposition. Yeah, this kind of called proposition. Oh yeah, and then important definition, which will also be used quite often. X is a set. And the power set of X is denoted P of X. And it is the set of all subsets of X. So the power set is a set of all subsets. Set of all subsets. If you see an example, it will be clear. Let's say A is a set containing 3 elements, A, B, and C. What is the power set of A? So it's a set of something, so it's going to be something like this. We have to write the elements of this power set inside this curly brace. So can you tell me subset of A? Yeah, empty set is always a subset of anything. And A, B, C, A, B, B, C. Maybe I need more space. C, A, C or C, A, it doesn't matter. And A, B, C. Did I list all the subsets? Yeah, these are all subsets of A. There are 1, 2, 3, 4, 5, 6, 7, 8 of them. The power set is like this. You list all of them. Oh yeah, one more question. What is the power set of empty set? Right? Yeah, it's right. No? It's right, only I made a mistake. Right? Yeah, empty set is a subset of itself. So power set of empty set has only one subset. Empty set is the only subset of the empty set, so we have only one thing. Okay, let's do one more thing, just to make sure that everyone understands this. What is this? Empty set? Oh yeah. Yes, this is it. Yeah, if you want, you can do more. Okay, let's not do that. Yeah. I wanted to say, maybe just for fun example exercise, you can try P of this. Because what this really is P of empty set, right? So you can keep doing this. Yeah, maybe you have to write. It's very easy to get confused, but yeah, it's possible. Oh yeah, just for a quick question. Just a quick question. If cardinality of A equals n, what is the cardinality of its power set? 2 to the n. Yeah. Think about this. Maybe we will prove this later. It's not that difficult. All right, so for sets, we learned how to compare them. Maybe they are equal or not, or is this a subset of this? And in mathematics, we do many operations. So for instance, numbers, think about numbers. Natural numbers, just 1, 2, 3, 4, 5, etc. These are just numbers. If you don't do anything with these numbers, maybe they may not be very, very useful. But what's useful, what makes it useful for numbers is that we can add 2 numbers or multiply, something like that. We can do operations on 2 numbers. 3 plus 5 equals 8. But if you don't do addition, if you don't do multiplication, numbers may be not very useful. but because we can multiply them, because there are operations, that's why numbers are useful, and you can apply this to many things. Similarly, for sets, we have operations. We want to operate on sets. By operation, what I mean by operation is as follows. Operation basically means you have maybe binary operation. You have two things of the same kind. Like, so think about numbers. Like I said, 3 plus 5. These are numbers, right? What is 3 plus 5? 8, which is also a number. So you want to operate. By operating, I mean you want to do something to create a new thing, which is also the same kind. Number plus number is number. But if you say 2 plus 5 equals apple, something like that, maybe it's not very useful. Maybe because you cannot do any further. So that's the idea, basic idea in general in mathematics. So operations in set, binary operations. So we have two sets like this. X union Y. We operate two. This is one way to operate on two sets. So we got two sets and we do something, we get another set. This is defined, this is definition. This is set of elements, X, such that X is in X and also in Y. This is the definition. Oh no, not or. Okay. Union is called union. And it's called intersection. Intersection. X intersect Y is X set of elements such that X is in the set X and also in Y. Intersection. And subtraction, X minus Y. Set of elements which is in X and not in Y. Okay? In the difference. So, an example. Natural. It's quite a natural operation. 2, 3, and 4. And what is the union of these two sets? You just combine them together. Just 1, 2, 3, 4, 5. Okay? This is the union. And intersection, you look at elements that are both in A and B. 1 is in A, but not in B, so 1 is not in this intersection. 2 only in B, so not there. 3 is both in A and B, so 3 is there. That's the only element in this intersection. Okay? A minus B. We want to find elements in A, but not in B. 1 is in A. Is 1 in B? No, so 1 is in this set. 2 is not in A, so you don't have to worry about that. 3 is in A, but also in B, so 3 is not in this set. 5 is here, not here, the 5 there. So you compute these 3 sets like this. So this is the definition of intersection, union, difference. Any question? Okay. So notice that maybe let's compute compute B minus A. What is B minus A here? 2 is here, not in A, so 2. 3, subtracted. 4, not there, so 4. These two are different. right? A minus B is not equal to B minus A. But it's quite easy to see that X union Y is equal to Y union X. X intersect Y. We will see this kind of thing later, but just remember. Okay. Now we defined intersection. We can talk about disjoint. If X intersect Y equals empty, then we say that X and Y are disjoint. They are disjoint set. That means they don't have any common elements. And also, if S is a collection of sets. Collection of sets, well, this really means just a set of sets. Collection and set, yeah, they are more or less the same. A collection of sets, or set of sets, in other words. Then we say S is pairwise disjoint, means maybe I can just forget about this. So S is suppose that S is a set of collection of sets, and S is pairwise disjoint means the following: for any distinct two sets in S, we have A intersect B equals empty. In other words, A and B are disjoint. If you take any two sets, they must be different, of course. If you take any two sets and they are disjoint, then we say that it's a pairwise disjoint. So maybe some example will be helpful. -1, -2, -3, and 0, 1, 2. Are they disjoint? Yes, disjoint. They don't have anything in common, the disjoint. And also 0, 1, 2, 3, 4, empty. So what is this? It's a set of sets, basically, a collection of sets. Is this pairwise disjoint? Yes, it is pairwise disjoint because just consider any two sets. Maybe this one and this one, they are disjoint. This one and this one, disjoint. Anything, any two, they are disjoint. So it's pairwise disjoint. So pairwise disjoint means something like this. If you take any pair, they are disjoint. All right. Yeah. One more definition. Okay. So at this time we will restrict ourselves to a subset of a given set. When we consider sets which are subsets of a given set, say U, then U is called a universal set. And or universe, a universe, just a terminology, universe. So instead of considering all subset or all sets, we just fix some set U and consider subsets of U. In this case, we will say U a universal set. And suppose that U universe X is a subset. Then U minus X, we know how to subtract two sets. We already run that. U minus X is called the complement of X. And also we also write in this way. U minus X can be written XC for complement or X bar. So they mean complement, which is defined to be the set U minus X. Okay, it's complement definition. So when we talk about complement of something, we must have the universe set already defined. Without this universe, this doesn't make sense at all. All right, when you have a universe, there is a very useful way to visualize sets called Venn diagram. So Venn diagram is very useful to visualize sets and elements. So for instance, let's say U is a set of integers 1 to up to 7, and A 2, 4. And maybe one more, 2, 4, 6. And B, say 2, 6, 7. Now we can, before doing this, let's compute the complement. What is A complement? It is U minus A, right? What are the elements in this complement? So you just remove 2, 4, 6. So 1, 3, 5, 7 is going to be the complement of A. B complement is what? You just remove this. So 1, 3, 4, 5. That's all, I guess. And so Venn diagram is this. So you draw U like this, and we have two subsets of U, so A and B. And then we have regions, and write elements here if they are in the intersection of A and B, if they are both in A and B. What is the intersection of A and B? 2, 6. So 2, 6 you write over there. And for the remaining parts of A, we write elements not in B. So 4 is not there, so 4 goes here. And here, the elements in B which are not in A are going to be the 7. And remaining elements will be drawn outside of this region. So 1, 2, 3, 4, 5. So this is the Venn diagram of these sets. So in this way, you can see, okay, A has 3 elements, B has 3 elements, 2, 6, 7, and A intersect B equals the set 2 and 6, something like that. So this is very useful tool to understand sets if there are not many sets. If there are more than like 3, then Venn diagram gets quite complicated. But anyway, for sets 2 or 3, it's useful. So we learned some operations on sets and Venn diagram. And when there are operations, there are usually theorem properties that these operations satisfy. For instance, for addition of two numbers, A plus B equals B plus A is simplest but quite useful property of the addition. We have that kind of thing for sets. So we assume that U is a universal set, and A, B, C are subsets of U, like that. First theorem is called Associative Laws. I'm not going to prove this. Maybe you are already familiar with this. I'm going to list them. B union C. So this means you take the union of B and C first. You will get a set. With the result, you take the union with A. And the thing is, this is the same as doing in a different order. And also the same thing true for intersection. This kind of property is called associative laws. And yeah, we do have, maybe it's it'll be how can I say, maybe helpful to compare these with operations you already know. For instance, plus. Do addition have associative laws? Do you understand what I mean? A plus B plus C, is it always equal to A plus B plus C? Yeah, we know that this is true. So this kind of thing is called associative law, and what I wrote here is that these are also true for intersections and union. Commutative law. A union B equals B union A. Also, A intersect B equals B intersect A. Try to compare these with this usual addition or multiplication or anything that you are already familiar with. 3, distributive law. A intersect B union C is equal to A intersect B union A intersect C. So it's kind of distributing A inside of this parenthesis, like that. So this is why it's called distributive law. And same thing happens for the other operation. You can also distribute A inside. Intersect A union C, something like that. Is this similar to something that you know? Yeah, just imagine A plus B, or okay, yeah, just C multiplied by this. We have C multiplied A, C multiplied B. So this kind of thing is called distributive law. It's similar. And identity. The names are not that important. You need to remember. You need to remember this. You don't have to remember all the names. All right. Wait. Yeah, this is of course correct, but yeah, I wanted to write something different. They are the same, right? I was a little confused. A intersect U, the universe set equals A. Yeah, this is what I wanted to say. So this is like a identity of this operation, like a 0 for addition. And complement laws. That means A union A complement equals the universe. A intersect A complement equals the empty set. 6. idempotent laws. A union A equals A intersect A equals A. Yeah. There are more to go. So I'm not going to prove this, but they are not difficult to prove. You can prove this using just looking at the Venn diagram, the regions of Venn diagrams. There's one way to prove this, or you can use definitions of these two sets being equal. But yeah, I'm not going to do that. 7, bound law. They will be quite clear. For instance, yes, A union, the universe will be the universe. It has everything. And A intersect empty set, you can guess it should be the empty set. And absorption laws. A union, A intersect B. What do you think this is? Yeah, just guess or tell me. A or B? Great. A intersect B union A or A union B. What is this? A or B? Yes. Easy, right? And involution law. A complement. If you take the complement of A, you get a set. You take the complement again, then you will get A again. You get back A. The complement of complement is the original set. 0, 1 law. Complement of the empty set equals A or B. Yeah, U, right? U complement empty set. And finally, let me write this over here. It has a special name to the Morgan's law. A union B complement equals A complement, but you have to change the operation. Intersect B. A intersect B complement, A intersect union B intersect. Do you think this is true? So what this says is that just test your intuition. This is a set of elements not in A or B. It must be out of A, right? Out of A and out of B, because it cannot be in A or B. So if you take the complement, it is not in A, and at the same time, it is not in B. So we have to take this intersection instead of union. That's why this is changed into this. The similar argument can show this. So remember this. Any question? Probably you have seen this before already. So now we learned the operation on two sets. Union operation. We defined the union operation on two sets, A union B. But we will define union of like many sets. You take the union of many sets at once. If, let's say, S is a set of sets, A1, A2, like N. Let's say S has N sets. So AI, each AI is a set. Then, sorry. Let's forget about this for the moment. If S is a collection of sets, so it's like the previous slide, A1, A2, etc. But it can be a set, a collection of infinitely many sets, not just finitely many. But anyway, it's a set of sets, basically. Then we say union of S. Can you guess what this is? So S, inside S there are many sets. You take the union of all of them. Can you write this? So it's something like this. So what does union mean? A union B means set of elements, which is either in A or B, or both. If X is in one of those sets A or B, we say that it is in the union. So it's something like that. So X is an element of what? Of some set. It can be just one or many, some set in S. Doesn't have to be all of them, just one or two, I don't know. Just if X is a set, X is an element in one of the sets in S, then it is in the union. And similarly, intersection, X is an element of every set in S. Okay? So maybe in this way it's a little hard to understand. So I go back to this slide. So just imagine that we have finitely many sets. S is a set of sets, A1, A2, etc., up to AN. Then what does S union S means? You just take the union of all sets. Maybe you can write this. Basically, this means this. Or, for shorthand, sometimes or oftentimes people use this notation. It's like a sigma notation. Union I goes from 1 to n AI. This just is a shorthand for this. All right? If it's finite. If it's not, it can be even infinitely many sets, but you can talk about whether this set is in every set of X or is this an element of every set in S, or is this an element of one set in S, something like that. So you can talk about this. Similarly, intersection is intersect A2 or equivalently using this notation. Okay. All right. Now let me give you a simple example just to make sure that everyone understands this definition. For I integer, let us define this set AI, set of integers greater than or equal to I. So it's a set of integers greater than or equal to I. And let's say S is the collection of AIs. It's collection of infinitely many sets. Do you get the situation here? A is defined like AI is defined like this. S is the collection of all of them. What is the union of S then? Union of this. A1? Oh yeah, A1, that's right. Because yeah, A1 contains A2, A2 contains A3, etc. Okay, that's fine. Or Z plus if you want. Positive integers, set of positive integers. A1 is. What is U? Intersect Z. No, not Z. S. What is the intersection of S? Think about this for 15 seconds. And then we can vote after 15 seconds. Or 10 seconds now. Ready for the vote? Yeah, if you want to vote, maybe I can give you some it's a multiple choice problem. Empty. Let's just have 2. Raise your hand if you think 1, or maybe 1 more. Yeah, maybe too late, but none of these. Okay, 1. Raise your hand if you think 1 is the correct answer. Okay? Now, raise your hand if you think 2 is the correct answer. Oh, almost as many as the previous one. Okay, so those who didn't raise your hand think 3 is the correct answer. So 3. Okay. Is there anyone who wants to explain your answer, your own answer? You can explain in Korean if you want. I can translate it for you. For those who raised for the first answer, why do you think it is the empty set? So if you're not, like I said, if you are not sure about this, that is probably because you don't really understand the definition completely. If you completely understand the definition, the answer should be clear. Or not? So what is the definition of this? It is the set of elements that are contained in every set in S. Can you tell me any element that is in every AI? Is there an element that is in every AI? Empty set? Empty set is not an element in A1. It is a subset, but we are talking about elements. Okay, by the way, let's consider this too. Is infinity an element of A1? Does A1 contain infinity? Really? Did I write A1 like A1, 2, 3, dot, 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 and then infinity? I didn't write this. Infinity is not an integer. Maybe you have some concept about the infinity, but it's not an integer. It's not a real number either. Infinity is not here. Infinity is not even in the first set. How can it be in all of this? Right? So this is certainly not true. Second, you can cross out the second one because infinity is not in the first set even. Actually, the correct answer is 0. Empty set. Because, okay, why? How can you explain that the answer is 0, empty? 네. Okay, so yeah, he explained very clearly. Okay, let me write this again. Suppose that, just for suppose, X is in intersect of S. Okay, just suppose. If you have a contradiction, that means this cannot have anything in it, right? What does this mean? X must be in A1, right? X must be in A2. For every I, it must be in AI. X is in A1. What can you tell about X now? What is X? Yeah, integer. So because of this, X is an integer or positive integer. Right? Because it is in A1. It cannot be an infinity or square root of 2, something like that. It must be an integer. Right? Okay, because this looks like a variable, let's say k. Just, it's not really necessary, but just to help you understand. Integer k. Is X in AK? Oh yeah, it is in AK. But is this in AK plus 1? No, because x is k is not in k plus 1, k plus, because k plus 1 only has integers bigger than k, so it cannot be in here. That means it is not here. So it's contradiction. It's a contradiction. Because we assume that x is in AI for every I, so we must have this as well. Because for all I, this means all. We must have this, but we had a contradiction. This is a contradiction. This means this must be empty set. Otherwise, we will have a contradiction. So this is the proof of the fact that this is, in fact, is empty set. Okay? So the correct answer was the first one, empty set. Any question about this proof? Okay, now here is another definition, set partition. Or simply a partition, we omit set and just simply partition. If it's clear that it's a set partition. A set partition of a set X is what? Is a collection of subsets of X. Is a collection of, let's put it this way. Subsets B1, B2, Bk. We don't know how many they are, but just subsets of X such that. This means such that. Yeah, just, okay. Non-empty. They must be non-empty subsets. We don't want empty for all I. I, of course, 1 through k. And we want to have non-intersecting, intersect j is empty for all I not equal to j. For different I and j, we don't want to have intersection. 3, their union is the whole set. So this is the definition of a set partition or partition. Okay, maybe this may look a bit complicated, right? We have many conditions. 3. Is this natural to you, set partition? If this is your first time to see this definition, you may think this is not very natural. We have many conditions, too many, 3, 1, too many, you say, right? Too many. But it is very natural definition in some sense. Have you heard of this word partition? Where did you hear this? Do you use Windows? You do disk partition, right? Let's look at this partition. So if you look this my computer, see you have 3. Physically, this computer will have only 1 physical hard drive, but there are 3 disks. How did we do that? How did somebody do this? They partitioned this physical hard drive into 3 parts, right? But when you partition your hard drive, you want to have some properties. They are exactly these. Let's go back to these slides again. So suppose you have like C, D, and E. We had 3 drives, right? C, D, and E. think of this as B1, B2, B3. Do you want to have the size of this is 0 byte? You partitioned your hard drive, and then you realize that, oh, the E drive has 0 byte. The size of the capacity of E hard drive is 0. Do you like that? You don't want that happen, right? Because you really want to use this. Okay? So this is essential for partitioning your hard drive. You don't want to have empty disk. There is no use for that. What about this? Okay. You partition your hard drive, and then you just used for several days, and you realize that if you delete something here, or if you copy something to D, it also copies the E. Or if you delete this, maybe a synchronize is kind of useful nowadays, but just for your local hard drive, that may not be very useful. Do you want that to happen? Some part of here overlaps with some part here. That's not going to be useful or efficient using hard drive, right? So you want to have disjointness of this. You want to use this region or this part only for E and this part only for D, no overlapping. So this is essential for that, right? And what about this? So suppose that you bought, like, let's say for simplest, maybe this would work. You bought 1 terabyte of hard drive. You partition this into 3. C drive has like 500 gigabyte, 200 gigabyte, and then 100 gigabyte. Then what would you say? What happened to my 200 gigabyte? You will complain to maybe the disk, or partitioning system, because we really want to use the whole thing. So disk partition is something like this. And in that way, those 3 conditions are very natural when you do disk partition. They are recorded over here. And we want to do that kind of system. Nothing is empty, no intersection, and the whole thing makes the original set X. So that will be easy to remember if you think about a hard drive, partitioning your hard drive disk. Okay? Now, do you feel these are natural? More natural than before? If you still don't think this is natural, yeah, that's fine. But mathematics is not just constructed out of nowhere. Mathematicians invented, or defined terminologies based on their experience, maybe in need of doing something. You can add additional condition, maybe A, B1 always has cardinality 1. That's fine. There's no bad thing about this mathematically, but there will be no use for this if your definition is random and arbitrary. But if you really define mathematical object carefully, that really reflect something in real life or problem that you want to solve, then one single definition can be very, very useful. So this is one example of that. And maybe, so we now probably understand the definition. Example, X is 1, 2, 3, up to 7. Let me define this P as follows. 1, 2, 4, 3, 6, 5, 7. Is this a partition of X? Yes. If you're not sure, go back to the definition and check every detail. P is a collection of sets. Are they all subsets of X? Yeah, they are subsets of X. Are they all non-empty? Yes, we don't have any empty set. Are they mutually or pairwise disjoint? This means pairwise disjoint. If you take any 2 different subset here, they don't have anything in common. And their union will be X. So it is a partition of X. This is a partition of X. So partition is something like this. And it can be very useful. We will use this later on. Very useful definition, concept in mathematics. Okay. All right, so set, what is a set? It is a collection of objects, but we don't want to consider their order, right? 1, 2, 3, 3, 2, 1, they're the same. We only care whether 1 is 1 there, is 2 there, something like that. But sometimes you want to consider the order. Sometimes you want to distinguish 3, 1, 2, and 1, 2, 3. So that means we need to have another definition. If you want to do more than just sets, then you need something different. So here is the definition for that. An ordered pair is, I'm not sure if this is a good definition, is a pair of, because I'm using pair again, pair A comma B of elements whose order matters. Let's just write this way. What I mean by this is that A and B are considered to be a different pair as B comma A. As said, if you use curly brace, they'll be the same, but they are different now because this ordered pair. Ordered pair means the order is important. And on n tuple, another definition, why don't we have more than just 2? Why don't we restrict ourselves to just 2? So n tuple, n tuple is an ordered sequence of n elements. Something like this, A1, comma A2, comma. So for n tuple or ordered pair, we use a round bracket like this. When I write a sequence using round bracket, it means it's an ordered tuple, and the order is important. We do care about this order. All right? So, 1, 3, 2, and we can have 3, 1, 2. They are different because their orders are different. And it's possible that we have repetition. This is an ordered pair. What is this? It's a 6 tuple. 1, 2, 3, 4, 5, 6 elements. They can be a repetition. It's fine. All right. Any question? So using n tuples, you can study the order of object. All right. So the question is, what is this n? Basically, to make it short. N is any integer less greater than or equal to 1. 1 tuple, something like this. 2 tuple is basically the ordered pair. 3, 2, 3, 2, 5, 4, something like that. You can have n tuple as long as you have n elements. It's an n tuple. N can be 1 or 2. So n tuple is more general concept than ordered pairs because it contains this. All right? Yeah. So yeah, n tuple. Now let me define Cartesian product of two sets. We have yet another operation on two sets, x, y sets. Definition. The Cartesian product of x and y is denoted x cross y, x times y, or it is set of ordered pairs, x comma y, where x is in x, y is in y. So this is the definition of Cartesian product. Example. If you see this example, you will immediately get the idea. All right, we have two sets, x and y. What is the Cartesian product x times y? So, in order to make this Cartesian product, you select one element from x, you select one element from y, you make a pair. So 1, A, 1, B, 1 and C, 2, comma A, 2, comma B, 2, comma C, like this. So these are all elements in this. Cartesian product is like this. Do you think it's true? Do you think this Cartesian product operation is commutative? Commutative means if you change this, the order, you get the same thing. Do you think, in other words, do you think this is true? Yeah, they are different, right? They are different. In general, they may be the same if the x and y are special, but in general, they are not true. They are different. Because y in this example, this will have a comma 1, something like that. This is not, a comma 1 is not in this. Because the order of the elements in an ordered pair is important. A comma 1 is not equal to 1 comma A, so it's not here. So they are different. So you need to remember this. And, okay, Cartesian product is a operation defined on two sets. Why not just, why don't we have, do we always have to have just two sets? Or can we extend this definition further? We can extend this definition, of course. We can have many sets, and then we can take the Cartesian product of many sets. So suppose we have n sets. So a set. The Cartesian product of them can be defined. How? It will be a set of, instead of two ordered pairs, you will have n tuples, A1, dot, 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 AN, where AI is in AI. I is from 1 to dot, 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 for every I. So this is the definition of Cartesian product of n sets. So as before, you take one element from the first set. Again, the order is important. And you take one element from the second element, a second set, etc. And then you make n tuple out of these, and then there will be one element in your Cartesian product. Okay, quick question. Let's talk about the cardinality. Let's say A is a set with 3 elements, B is a set with 4 elements. What do you think the Cartesian, the cardinality of their Cartesian product? A times B, Cartesian product. 12. You just multiply them. Because to make an ordered pair, you need to select one element from A, one element from B, and they are independent, so you can 3 ways to select one element from A, 4 ways to select one element from B. So this. So actually this is a theorem. Very simple theorem, but still. A cardinality of this is equal to this times B. Right? 12 equals 4 times 3. All right? This is true. Now, another question. For implicit, to make it explicit, let's say A is 1, 2, 3. What is the Cartesian product A times empty set? Okay, think about this for 10 seconds and we can vote. Yeah, I need to think about the possible answers. None of this. Okay. Are you ready? Yeah, raise your hand if you think 1 is the answer. Don't look at, just be, yeah. You don't have to look at other people. Maybe, shall we close our eyes? All right. 2, if you think 2 is the answer. 3. Oh, 3, okay. There are some people. If you think 3, none of these are correct, then what do you think the answer is?
This is empty set.
Mm-hmm.
So the Cartesian product is not a set. So I think then this is not a set.
This is empty set. So Cartesian product is not a set? Not defined, you mean? Cannot defined. Okay, let's go back to the definition. I think this is a good point. If you have some idea, it is very useful to share your idea. Other people can learn from it, or you can really understand this better. Okay, let's go back to this definition. X and Y are sets. I didn't mention that X is not, they are not empty. I didn't say that they are non-empty. Yeah, so that means they can be empty sets. Even for empty sets, Cartesian product is defined. So they are defined. So if you're not sure what the answer is, go back to the definition and just follow the definition, line by line. Don't think about just, so the main problem that many people who don't like math is this. Don't look at the definition and just think by themselves, oh yeah, this will be this, and just go for this. Their intuition. Maybe sometimes intuition is useful, but it is only useful when you have the solid background in your definition. Even if you don't understand the definition, intuition doesn't do anything good for you. So, go back to the definition. X times Y, the Cartesian product, is a pair X and Y. What is X? You select one element from X. You select one element from Y. Okay? Let's just use this definition here. Go back to this definition, maybe in the next page. A is 1, 2, 3. Okay, let's say B equals empty. A times B is Y. I'm just copying the definition, only using different letters, doesn't really matter. You take one element from A. You take one element from B, and then you make a ordered pair. Can you do that? What is B? You cannot find B. If you cannot find B, what can you say about this? There's nothing. This is in this set only if you can do this. There's nothing here because you cannot select anything from B. So it has nothing in it. This is by definition. I didn't use any intuition or like clever idea. I just follow the definition and it will be just clear from the definition. So empty set or this kind of statement is very confusing at the first time. So in that case, just go back to the definition and follow the definition. That will tell you the right answer. But if you just think about what this should be, maybe you're wrong because you think this set should be something like you have something in your mind, which may be different from the original definition. Okay, so always go back to the definition, then everything will be quite clear. Any question about this? So the correct answer is empty set. All right, so we learned many things in set. Oh yeah, by the way, actually, you can guess this from this theorem, right? What is this? This cardinality is this times this. Apply this over here. Cardinality of this must be equal to the cardinality of A times the cardinality of empty. Cardinality of empty is 0, so 3 times 0 is 0. So yeah, it must be the empty set.